Okay, I have shared my screen. Can you see the screen clearly?
Yes, sir.
Yes, sir.
Right. Okay. So let me share. So, okay. Right. So this is the fifth lecture, actually, fifth day, and it's the third lecture. And we did introductions to movement of architecture completed. Then contemporary works of sustainable architecture. We have looked at several architects' works, and we have started with the fundamental concepts of sustainable design. So we discussed context, materials, and lighting. So today we are going to complete the part that is interior lighting. That is the plan. So always remember that 40% of human impact on environment is due to buildings, and we have to reduce the footprint of humanity to the size of the Earth. So that is the key target of doing everything. So we discussed these things in order to reduce the footprint of buildings, how to work with the sunlight, how to work with context, and so forth. We have to discuss wind in the next session. So that is where we are now. So this is what we did. So today we will start with sustainable lighting. I mean the artificial lighting. In order to be able to design lighting, I'm talking about architectural lighting in a sustainable manner. I think the most important thing is to understand light in the fundamental level. So what is light, how light is generated, and so forth. If you have a fundamental understanding of that, then you will be able to do it in a sustainable manner. So we will make that kind of attitude towards learning lighting today. Okay, so we will begin with waves. I think everybody knows you learned waves in your A-level physics and so forth. So this is a general wave equation. If this is a wave, if you don't remember, the length between a top or the crescent or a valley is lambda. So that length is called lambda. And that is the wave length. And the height of the wave, you remember, is the amplitude of the wave, and that is called A usually. There's a term called frequency we have defined, and you remember, I think everybody remember this equation, V equals frequency times the wavelength. So that is the definition of the frequency. Frequency is 1 over T, the time taken by the wavelength, one wavelength to pass. The distance of a one wavelength passing is called, that is time taken is the frequency. So that is the fundamentals of waves, better to know that. If I give you the speed of light to be 3 million meters per second, if the frequency, say what is the frequency of an electromagnetic wave of a wavelength of 10 meters? So can you calculate this? Who is going to do it fast? So use this equation and then just tell me what is the frequency of this wave. This is an electromagnetic wave with a wavelength of 10 meters. It's a very long wave. So what is the frequency?
Frequency equal to 3 into 10 to the power 6.
Right. Okay. So what we'll do is if frequency then is equals V divided by lambda. So V is this this divided by 10 meter. So what will happen is the 1 0 will go here, and the answer is yeah, it's a very high frequency. Okay, so you can do it. It's a simple thing. So light. So when you come to light, James Clerk Maxwell is the one who introduced light to be electromagnetic waves. So what he did was there were equations and experiments done by other scientists at this time about electricity, about magnetism, and so forth. So what he did was he just gathered the important equations and put them together. So these are the 4 Maxwell's equations. I think we need not to go into deep into that one, but just to recap your A-level physics, the Gauss's law, that is the curl of the electric field is the charge density. So the curl of the magnetic field is 0. That means magnets come in dipoles, so there are no magnetic monopoles. Then the cross product of the curl and the electric field is is proportionate to the change of the magnetic field. So there's a relationship between the electric field and the magnetic field. So when you change the magnetic field, electric field is generated, and then Ampere's law, that means the vice versa. So when there's a change in the magnetic field, there will be a current discharge. So there's a current density comes out of a change of the magnetic field. There's a relationship between electricity and magnetism. So when he worked out these equations, when you fiddle with that, he found that it comes up with the kind of a wave. So which he identified as an electromagnetic wave, and he found a way to generate these kind of waves using an antenna. So this is his description of the wave. So this is if this is a space dimension x, there's one electric field that is going changing like that, and then there is a magnetic field perpendicular to that one going changing like that. That was his description of the electromagnetic waves, and he calculated the speed of these electromagnetic waves, and its value, its speed was given by, according to his equation, this is the square root of permeability of free space and permittivity of free space. So these are, permeability is related to magnetism, and the other one is related to the electricity of the free space, the electric charges of the free space. So these are qualities of space that is calculated based on electricity and magnetism, and they have nothing to do with light. But when you calculate the speed mathematically, it came into this number, and he recognized that is the calculated speed of light those days. So there was a very strong evidence that light is an electromagnetic wave. So with that, many of the waves we know became only one thing. For example, radio waves is an electromagnetic wave. The FM, AM, TV, all those are radio waves. And they are one particular wave. There are all different kinds of waves. They are just the electromagnetic waves. Only thing is they are at a different wavelength. So an AM channel wave is usually about 100 meters long. So your radio, if you tune it into AM, so that is about 100 meters long wavelength. The FM channels are about 1 meter long wavelengths and so forth. So what we call infrared light is all about 0.1 centimeter like, and about 1000 nanometer, like that range of the electromagnetic waves are called the infrared waves. And what we call X-rays are about 0.1 nanometers to 10 nanometers. So there is ultraviolet rays, and you are hearing about gamma rays. All these are electromagnetic radiation and nothing else. And visible light is in this spectrum of radiation is this small tiny part that is approximately between 400 nanometers to 800 nanometers. So this range is the visible light. So visible light waves have colors, isn't it? So from where does these colors come from? Who can tell? So unlike X-rays or radio waves, they don't have colors, but the visible light has colors. So the visible light has a blue color, visible light, red color, visible light, and so forth. From where does these colors come from? Why these frequencies have colors?
Because we can only see that that part of the frequency range.
Yes, true. But why, let's say, 400 nanometer frequency has a violet kind of a color? From where does that color come from? Why don't you try?
I think that color is provided within our mind.
Exactly.
So
yes, there's no colors in light. There's only frequency. So color is a conscious way of interpreting that frequency. So when you say 700 nanometer wave, it's only 700 nanometer wave, nothing else. It doesn't carry color with it. So color is a conscious interpretation of that wavelength. So just remember that. So that is how colors come. Okay, now about spectrum of light. So when there's a light source and when you send it to a prism, we see a spectrum like this. So if you send sunlight through a prism, I think you know, you have seen this many times. So there's a spectrum. One thing scientists notice is if you take a gas bulb or gas cloud, let's say hydrogen gas, and if you send this kind of a light, let's say sunlight through that hydrogen gas, and look at the spectrum again, you will see several particular lines of colors are missing. So you take a gas bulb and you send sunlight through that, and then send that light through a prism and see what is the spectrum. You see some lines are missing. So let's say we use hydrogen. So if you use the same hydrogen, put it into a bulb, you heat it up, or you send electric arc through that one, and you make it excited and let it produce light. And if you look at that light through a prism, you see whatever the missing lines here are appearing on the spectrum. So this is called the spectrum of absorption. And this is the spectrum of emission. So it is wonderful to see that what is missing here is what is coming here. So you can try with different gases. You can try with neon gas. You can try with xenon gas and so forth. Exactly what is missing in the absorption spectrum is what is visible in the emission spectrum. So what is absorbed is what is emitted by these gases. So these are the absorption spectrum of hydrogen. So you can see 1, 2, 3, 4, about 5 visible lines are missing, and exactly the same lines you can see when you light up a hydrogen gas bulb. This is helium, so you can see there are several lines, and what are the missing lines here appears exactly when you take the emission spectrum. So by theory, then we can conclude if there is a gas that absorbs all the light that comes into it, and if it emits nothing in its spectrum, then in theory, when you heat it up, it should emit all the spectrum. So what will happen is, if it absorbs everything here, then when you heat it up, it should emit entire spectrum there. And people thought that is what's happening in the sun and so forth. So that is not exactly what happening in the sun, but that kind of a gas or that kind of an object is called a black body. So it's a theoretical object that absorbs entire radiation spectrum that falls into it. And because of that, in theory, when you heat it up, it should emit the entire spectrum of radiation out. So black body radiation is very important for architectural lighting, because in the earlier times, the artificial lighting was filament bulbs, and everything was decided based on the filament bulbs light. So when you heat up anything, let's say you heat up iron or aluminium or anything, the glowing color of that material, if it is a solid material, when you heat it up, the glowing color of that material only depends on its temperature, and it has nothing to do with the material. So that is something you can observe. So if you put iron in, let's say, a ceramic core and or a ceramic kiln, and if you heat it up until it becomes red hot, the color of the core, the ceramic core, and the color of the metal is the same. So whether it is ceramic, whether it is metal, whatever it is, the emitted color of light depends on its temperature. So that kind of object, metal is not a perfect black body, but if you consider it as a black body, so a black body's light emitted totally depends on temperature. So this is how a black body's temperature depend. I mean, the color of the emitted light of a black body depends on its temperature. So if you heat up, let's say this is iron bar like this. So when you heat it up to 1000 Kelvin, so you will get this kind of a reddish color. And as you increase the temperature, when you go somewhere near 900, it becomes kind of a bluish color. So in between around 6500, there is kind of a white light. So this is the black body radiation. And those days, when you light up incandescent bulb like this, a filament bulb, the temperature of the filament determines the color of the light. So when you select a light bulb, the color of the light bulb is determined by the color temperature. So that is called the color temperature of the light. But nowadays, because we are using not only filament lights, we use very, very different kind of lights, the LED lights and fluorescent lights and so forth. So it is no more called the color temperature. It is called the correlated color temperature, CCT. So whenever you select a light bulb for interior lighting, you have to look at the CCT, the correlated color temperature. So you, even when you go to a hardware to buy a light bulb, they will ask you what kind of color you need. Is it daylight? Is it warm light? So the convention is the lesser hot one. Let's say 3500 is called the warm white light, and when it goes to this region towards the blue side, it is called the cool light. So that is the concept of correlated color temperature, CCT. So this is how the color is used by interior designers and architects. So this is the convention. Usually for living spaces, you use this kind of a range, particularly for tasks, for reading, for writing, for office work. We use 3500 Kelvin to 5100 Kelvin, this particular range. So this is how lights are selected. For wine bars, for decorative purposes, they use around 2500 Kelvin light. And for commercial and industrial works, we use the range around 4000 to 20,000 Kelvin. This range is used only for that. So what you must remember is for task light 3000 to 5000. For retail, you can use a little bit more bluish range light. So this is how light is used. So just remember, warm, when they say warm white light, that means something like this, around 3000 Kelvin. A white light means about 5000 Kelvin, and cool light means about 6500 Kelvin. So this is the range of color of light. Correlated color temperature, CCT. Okay. Then this is also something very important, the black body radiation. James Clerk Maxwell, after the James Clerk Maxwell, there's another Maxwell coming to lighting, that is Max Planck. So what Max Planck's task he was given was to create a filament light. He has to identify the correct temperature that provides the best lighting output. So he did experiments with black bodies, heating up black bodies, and he came up with this particular graph. So if you heat a body around 3000 Kelvin, so this is the electromagnetic radiation that emits by that time. This range is the visible light, and this is infrared, and this is ultraviolet. So you see this kind of a graph. 5000, it's something like that, and 6000, it's like that. And if you heat somebody around 7000, it's going like that. So it is known, or it is believed those days, that the amount of energy carried by a particular frequency is proportionate to the temperature. Sorry, the amount of energy is proportionate to the frequency. So as the frequency increases, so the wavelength reduces, it is going on a parabolic curve like that. So these were parabolic curves. But what Maxwell's noticed was that after some point, that parabola doesn't continue, it falls down. And there are hardly any radiation given out that is close to, let's say, 100 nanometers. There's almost nothing. So this dropping here was a miracle and it cannot be explained. So what he found was, in mathematical terms, if you think that energy is not just proportionate to the frequency, but energy is proportionate to the frequency with an integer number called n. So n is 1, 2, 3, 4 kind of an integer number. It's not a 1.5 kind of thing. It's an integer number. And h is the Planck constant. So when you consider it like that, this graph can be explained why this is happening. So then came Einstein, and I think you know his explanation of photoelectric effect and so forth. So what Einstein showed is light is a wave, that is true, but light can also be described as a quantized thing that comes in kind of packets. So light energy is quantized. And Einstein explained what is going on with the Maxwell's thing. So according to Einstein, he explained that space-time is quantized. So space and time comes in a discrete quantities called Planck lengths and Planck time. So it's a kind of a grid. Space-time is kind of a grid that is made out of units of Planck length and Planck space. And that is why this is happening. So he said, then E equals HF. So energy is equal to Planck constant time frequency. So this is the Einstein's equation. So he said energy is equal to Planck constant times the frequency. So then this is something important about lighting, because the light comes with the electrons falling from one energy level to the another energy level. So Niels Bohr. So this is the model of the atom that was before Niels Bohr. So there is a proton and then there's an electron that is orbiting around. And the problem with this model is that when the electron orbits around a proton, because it is undergoing an acceleration, it should emit electromagnetic radiation, and it should lose energy, and it should spiral and fall into the proton. So that why it is not happening cannot be explained. But what Niels Bohr found is if the light energy is quantized, if light is coming in packets and not as water or liquid, it's not coming as a continuous flow, it's discrete units. So if light is coming in discrete units, then this electron cannot absorb any amount of energy, or it cannot release any amounts of energy. It has to emit energy in discrete packets. So this electron cannot continue losing energy and then fall into the proton, because the amount of energy it can emit is quantized. So this is the Niels Bohr's atom model. So there are several postulates he used. One is the electrons orbit around the proton in circles, like the planets go around the sun and the moon. So this is a postulation. It's not exactly true. The second one is the angular momentum. So that is the important one. The angular momentum of an electron is given by, this is the angular momentum, and this is the Planck constant divided by 2h, so which is called h bar actually. So angular momentum is quantized. That means there's an integer number. So n is 1, 2, 3, 4 kind of numbers, and this is a constant. So angular momentum is quantized. So that is all about Bohr's model of atom. And in the university, what I used to do is I am giving this exercise for a particular purpose for the student to calculate together. So since you are not together, I will not do that. I will just explain what it is. So let's say this is the atom. So this is the proton. Let's say this is a hydrogen atom. This is the proton, and then this is the electron that is orbiting around the proton. So according to Niels Bohr, the angular momentum of this electron is given by L is the angular moment, n times h divided by 2 pi. And by basic physics, we know the angular momentum is the mass times the velocity times the radius. So MER is the angular momentum. And it is by definition, that is what is called angular momentum. And then the force between the electron and the proton, so that force is the one that drives this in a circle without allowing it to escape. So that force by theory is m times the velocity squared by r. So I am not going to prove it. Look at your A-level physics books, it is there. So that is the angular momentum of anything that is rotating round. And then the Coulomb law. So there's a charge in electron that is a negative charge, and there is a positive charge in the proton. So there is a attraction between them. That attraction is the thing that makes it go around like this. So that attractive force is calculated according to the Coulomb's law, which is now this is almost equal to the gravitational law by Newton. So this force is Q1 is the first charge, Q2 is the second charge. If the distance is r, then Q1 times Q2 divided by r square. So when you multiply it by a constant, you get the Coulomb force. So this is sufficient for you to calculate the radius, this particular radius of the hydrogen atom. So I have given K here, so this is the K. So I ask you students to use this number, and then the charge of the electron is 1.6 times 10 to the power minus 19. And then the mass of the electron is this. So these numbers are enough for you to calculate the radius. So radius, you can see, comes in integer numbers. So there's no one particular radius. When you add different numbers to n, it will give different radiuses. So students do calculate. So for you, I will do it by myself. The first way of doing it is angular momentum according to the Niels Bohr is this, which is equal to this. Okay. So MVR is here. That is this one. And this is the same thing here. So MER equals NH divided by 2 pi. So we will take V out. What we'll do is we'll divide this by M and R. So we will get the V. So V is NH divided by 2 pi MER. So that is the first term. Second one is this Coulomb force is the centripetal force. So these two are equal. So K times the charge of the electron is equal to the charge of the proton here. So K times, if the charge of the electron is E, K times E times C divided by R square. So this thing is equal to the centripetal force mv r square. Simple. So we can take V from this one also. Actually, it is V squared is better. So we will take V squared. What we'll do is we will put M and R this way. So this 1R gets cancelled. So KE squared divided by MR is V squared. So we have V here and we have V squared here. So we can compare V squared. We can remove V from these two. So square of this equals to this one. So KE MR is equal to square of this one, which is n squared h squared divided by 2 pi square becomes 4 pi square. m squared plus r squared. So m cancels, 1r cancels. And if you take r out of this and put k squared downstairs, r becomes n squared h squared divided by 4 pi squared m k e squared. So that is the radius of the hydrogen atom. So you can plug in these numbers here. That's what we were used to do in the university, and calculate the r. So you can see n is an integer number. It goes from 1, 2, 3, 4, and so forth. So we have different numbers for r. So r1 will be one number, r2 will be another number, and so forth. What I'll do is I will leave this as an exercise for you to calculate at home. So just apply these numbers here and put 1, 2, 3, 4 for n, and then calculate the radiuses of different electron orbits of hydrogen atom. Okay, then what I'll do is then I'm giving them another one equation, that is the Coulomb law about energy. So if you take an electron orbiting around the nucleus, the total energy of this electron is equal to the kinetic energy plus the potential energy. Half m squared, that is the kinetic energy, plus potential energy. The Coulomb law says the potential energy between two charges is the k times q1 q2 divided by r. So this is Coulomb law. According to that, this is the energy between two charged particles. So we can bring this as the potential energy here. So energy of this electron will be, the potential energy will be k times plus E for the proton minus E for the electron. So plus E times minus E becomes minus k e squared, and the distance is r. So this becomes minus k e squared divided by r. And half m squared, I think we calculated this earlier. We have m squared here. So we can put v squared, actually we can take v squared here. From this one, we can bring m here, and v squared is k e squared over r. We'll put it here, k e squared over r. And then this becomes half k e squared over r minus k e squared over r. So the total energy of this electron is minus half k e squared over r. Okay, now with this simple equation, because you calculated different numbers for r earlier, you can calculate potential energy of different energy levels. So not only potential energy, total energy. So if we take this is the orbital 1, orbital 2, orbital 3, orbital 4, and so forth. So what is the energy of each orbital? So you can calculate what is the total energy of orbital 1, 2, 3, 4, and 4, 5. So according to Niels Bohr, what happens is when an electron falls from one orbital level to another orbital level, it has to lose energy. So it emits an electromagnetic radiation. Vice versa, when electromagnetic radiation falls into an atom, the electrons get excited and it's uplifted to a higher energy level, absorbing that energy. So that is what is going on. So I ask students to calculate the energy that is put out when an electron falls in the hydrogen atom to the energy level 2 from above levels. So it is, I'm omitting energy level 1, I'm asking energy level 2. So what will happen? An electron falls from energy level 3 to energy level 2. So you can calculate the total energy of energy level 2, you know, total energy of energy level 3. So just deduct 3 from 2, you will get what is the energy when an electron falls from the energy level 2 to 1. Sorry, 3 to 2. Then what happens? 4 to 2, 5 to 2, and so forth. So what is the energy that is emitted when electrons falls from above levels to the energy level 2? So I give this as an exercise. So you can do it at home and just fill this up. And if you know what that energy is, you can use Einstein's equation, E equals hf. Energy is proportionate to the h times the frequency, and calculate what is the frequency of light that is emitted when an electron falls from upper level to energy level 2. So what is the F1, F2, F3, F4? So students fill this usually, and then using the wave equation, V equals F lambda, we can calculate what is the wavelength easily. So you can fill what is F1, F2, F3, F4, and what is lambda 1, lambda 2, lambda 3, lambda 4. And then why this is important lighting is what I do is I project this to the screen and to the whiteboard, and then I will ask students to come and mark the frequency or actually the wavelengths you calculated here, the lambda 1, lambda 2, lambda 3, lambda 4. So they come here, they mark in different places. So I give this as a group exercise, and then what I'll do is I'll project the actual wavelength of hydrogen atom. So this is the spectrum, the emission spectrum of hydrogen atom, and usually by like a miracle, everything matches here. So 656, 486, 434, these numbers matches. So then the students get the feeling, my God, this is what is actually going inside atom. So we didn't use we just use mathematical calculations, the angular momentum, the frequency, the mass of electron, and so forth. And we did this calculation, and it is miraculously matching with the spectrum. So you get the feel that this is actually what is going inside an atom. So why this is very, very important to understand in lighting is this is how different frequencies are emitted in the hydrogen atom when an electron falls from energy level 3 to 2, we see red light. Energy level 4 to 2, we see a blue-green kind of a light, and energy level 5 to 2, we see a violet light. So what happens if electron falls from energy level 2 to 1? Or energy level 3 to 1, what will happen? No, we can't see that because that is that will be a high frequency one. So that will be infrared light. So we will not see that. Similarly, if anything falls to energy level 3, that will be ultraviolet. So we will not see that also. So what we see is the electrons falling onto this energy level 2. So these things is what we see as a band here in the hydrogen atom emission. Okay, so this is the visible spectrum. This is the light we see. So if you take sunlight, and this is what we see, and you can see there it's getting darker here and darker there. Why is that? It is because the sensitivity of our eye, our visual system gets gradually impaired when you go to these two extremes. So we see bright light here and we don't see much light there and much light there. It's not because there's no radiation coming out. The radiation comes out, but our eyes are not sensitive to those radiations. So they become darker when you go to the corners. So this is something important to know when you come to lighting. So we will discuss why it is in time to come. So about gas emissions, the emission radiation, the spectrum. So this is hydrogen, and then this is neon, and this is iron. So why when it comes to neon, you have more lines, and why you have much more lines when it comes to iron? Yeah, can Ruan answer that?
So because iron has more elements than other two?
Yeah, iron has more electrons than hydrogen. So you have different electrons from different levels. So they have different energy levels. So much more energy levels are there. So you get much more spectrum of light than hydrogen. Hydrogen has only one electron, so it has only these things. Actually, Niels Bohr's model only works for hydrogen atoms. So when it comes to other atoms, it doesn't work. We need the quantum mechanical model to explain them, and that is a far more successful model. Right. So that is the basic theory understanding I require from you, and it is important because you are talking about bulbs, gas bulbs. So this is neon bulb, and this is the spectrum of hydrogen. This is the spectrum of helium, and this is lithium, and this is the oxygen, and then this is nitrogen, and this is neon. So you can see as we go down in the periodic table, we get more lines in this spectrum. Now, what is the problem we have? Let's say in your reading room, if we use hydrogen lamp to light up, let's say we use a very bright hydrogen lamp to light up our living room. What is the problem with that? Can you recognize a problem?
It's emit the blue, the three colors where it's there.
Exactly. So
the rest of the colors, yeah.
Yeah. So the problem is it emits only those few colors. So your room will be very brightly lit up. But when you look at colors, you don't see the colors. You see only if there's that particular color, you will see color. Otherwise, you will see the light and shadow you will see, but you will not see colors properly. So that's a big issue. So for example, that's why the high-end cars like Volvo, they use xenon bulbs. So xenon is very much down in the periodic table. So it has a lot of lines like that. So you have some better quality of color rendering. So these are the spectrums of different light sources. So for example, this is the spectrum, exact spectrum of sun, and this is hydrogen, this is helium, this is the mercury. So that concept is something very important in lighting, the color rendering index. So we can't use lights. So for example, these hydrogen lights, the neon lights, and particularly some halogen lights are very energy efficient, but we can't use them for interior lighting because they don't have the sufficient color rendering ability. So there's a thing called CRI in bulbs, that is color rendering index. So when you are selecting a light source for interior lighting, you have to look at the CRI and then select. So this is something important. And you have to consider the function of the space as well. So if it is much more related to color, the CRI index is also not enough. So we will discuss other indexes that has a grading of a broader color spectrum. So for the time being, we look at CRI, the color rendering index of lights, and then we select lights for interior lighting. So unless you understand this concept of color rendering index, the spectrum we discussed, you will not be able to select lights in a sustainable manner. That's why I took that time to explain that to you. So if you look at the incandescent or halogen lights, they have a very good color rendering index. The filament lights have a very good color rendering index, so it is around 100. So triphosphorus fluorescent lights color rendering index vary from 90 to 80 depending on the materials used and the design and so forth. The metal halide lights have around 85, and then fluorescent lights have about 70 color rendering index and so forth. Usually for interior lighting, we have to select a light that has more than 85 color rendering index. So that is the norm. So if you look at low pressure sodium lights and clear mercury lights, so they have very, very poor color rendering indexes, so 5 and 17. So we cannot use them for interior lighting, although their efficiency or the efficacy is high. So these are some of the lights we can use for lighting. One light is the low pressure sodium lamp. So how this lamp works is, so there's a discharge tube there. So inside that we have the sodium. So when an electric arc is produced inside that, the sodium gets melted and then it vaporizes. And that sodium vapor starts to glow. That is how the sodium lamps work. And then this is the spectrum of a usual sodium lamp. Then there's high pressure sodium lamp. So if you increase the pressure inside, now this is the bulb, and inside that there's a tube like that. So inside this tube is where this discharge happens, and the sodium is inside this tiny tube. So if you increase the pressure inside this tube, the spectrum gets little bit improved. And then we see in the market mercury lamps. So street lighting and so forth, you have noticed it is the mercury lamps that are used. So even in mercury lamps, the problem is if you reduce the pressure inside this mercury bulb, it works almost in the same manner like the sodium lamps. So there's mercury inside this tube. So when there's electric discharge between the anode and the cathode, this mercury gets vaporized and it starts to glow. So if it is atmospheric pressure, this is the wavelength spectrum that you can see. So if it is very low, let's say the pressure is 0.0005 atmosphere, like we can see there's only one wavelength that is coming out of this mercury lamp. And if you increase the pressure like this to 200 atmospheres, we see a slightly better performance like this. So when you are selecting a mercury vapor lamp, always look at the pressure. What is the pressure inside the gas chamber? Then in the market, you see these lamps that are called metal halide lamps. These are some improvements to the mercury lamp and nothing else. The only thing is in this gaseous chamber, there are some metal halides like bromine or iodine is there. So that improves the spectrum output of these lights. Okay, so this is the lights we are going to discuss. The incandescent and halogen lights, so they have excellent color rendering properties. And this is the limit from where it is not recommended for living spaces lighting. So triphosphate fluorescent lights, they are not usually recommended for interior lighting, but they are at the margin. Metal halide lights are not recommended, but we can use in some areas of interiors. Fluorescent lights are not good, it's about 70. Then coated mercury lamps have a little bit better color rendering index than normal mercury lamps. Then high pressure sodium, then clear mercury is 17, and the low pressure sodium lamps have a very poor color rendering index. So just have a general understanding about these bulbs that are available in the market. So out of the lights, incandescent lamps have a very good color rendering ability because they are solid. So they are like sun. So they have the entire spectrum range available in them. So this is the spectrum of a tungsten filament light. So it's something like that. So if you compare it with the daylight, you can see it's almost the same thing. And in the market, other than tungsten filament lights, there is another lamp called the halogen lamp. So difference with this halogen lamp and the tungsten filament lamp is, now this is a halogen lamp, so you can see inside the bulb there's a secondary another bulb like this. The problem with the filament lamp is the tungsten in the filament gets evaporated and they get deposited on the bulb surface. So when you look at a bulb in a few months time, you can see these deposits of tungsten in the bulb surface, inside surface. So when you add some halogens to that one, so we cover it with the secondary bulb like this, then if you put some halogens, let's say bromium, iodine kind of things, so halogens will make a chemical reaction. It will bring the deposited tungsten and deposit it back on the filament itself. So this light has much more better lifespan for the light, plus the spectrum also gets a little bit improved. And then we see fluorescent lights in the market. So how fluorescent lights works, I think you know. So there is an electric discharge from anode to cathode, and with that discharge, there is a kind of a mercury mixture, mercury and then some other improved materials mixture, a gaseous mixture is there inside. So what will happen is that mixture get excited and it emits a kind of ultraviolet radiation, which is not visible to human eye, and the glass tube, perimeter glass tube, has a phosphorus coating on it. So when the ultraviolet lights get onto that phosphorus coating, it gets excited and then it starts to emit visible light. So that is how the fluorescent lights work. So this is the spectrum of fluorescent light. It is not so good. And then when it comes to LED lights, they also have a very good color rendering index. So we can use them for interior lighting and so forth. LED lights work with this electron holes concept, how it works. And I am not going to explain you how anodes, how these diodes work and so forth. So I think you know how it is, but this is the spectrum. So in comparison to daylight, this is the spectrum of a typical LED light. So these are the comparisons of spectrums. So this is daylight. This is incandescent light, the filament bulb, and it is the same with the halogen here. Halogen we discussed is only some addition of iodine or bromine to the same filament light. It's almost the same. And this is fluorescent light. You can see this is the spectrum of fluorescent light. This is the cool white LED. This is the spectrum, and then this is the warm white LED. So these are the spectrums of different lights. So when you're selecting light for an interior lighting, one thing you must look at is the color rendering index and its spectrum. So in the market, when you buy a light bulb, look at what is the CRI index. But if you select lights for particular color related tasks, the color rendering index CRI is not sufficient. So there's another index called CQS, the color quality scale. The difference is in CRI, these are the colors they specifically check for color rendering ability. But CQS, there's a very wide range of colors. So this range of colors are tested and then they give this CQS certificate. So when you select a light bulb, look at the CRI index and the CQS index of the light. So that is important. So that is about the quality of light. So everything you should know about the quality. The important thing is not the quality. Quality is also very important, but in terms of energy usage of lights, it is the quantity of light, how to manage it, and so forth. So, is there any questions you can ask before I get into the quantity calculation of light?
So I have a question regarding the previous calculation. The
Okay.
charge of the electron and the protons are same. We are putting at E square.
Charge of the electron and the proton is almost the same for our calculations, but nowadays the scientists say there's a very slight difference, but we will consider for our purpose as equal.
Okay.
Right. They cannot be equal. They are not.
Yeah, cannot be equal. Yeah, that's it.
They are not manufactured in the same factory, isn't it?
Yeah. And another one, how the electron fall from one energy level to the another energy.
It is all about
just get the energy and go to the next level and release the photon and come back.
Yes, that is what happens. So that is how we see things. So if you look at your table, how you see your table is the light comes from the light source, falls into the atom of this table made out of, and what will happen is some of the electrons will fall into upper energy levels, and then when those electrons fall back, they will emit electromagnetic radiation. So that is the color you see on the table.
Okay.
Right. So the way I explain, is it too much for you? I don't know. I assume that all of you are engineers or quantity surveyors at least, and you have studied physics and maths for your A levels, and I think you can understand what I say. If not, just tell me. So even if you can't do those calculations and so forth, if you just basically understand the concept behind that, the concept of the color rendering index, the concept of black body radiation, so that is sufficient. No? Okay, so shall we move forward then?
Okay.
Right. Okay. So we will go forward. So if this is boring or if you can't understand, just tell me. Don't worry. Only few of us are here. Just raise your hand and then tell me. Yeah? Right. So we will proceed. So then that is all about the quality of light. This is about the quantity of light. So when you light up a space, we need sufficient amount of light. So how to calculate that? So that is all about this. So there are several concepts involved into that one. One is the illuminance. We talk about a concept called luminosity. So luminosity is the amount of energy produced by a light source. So let's say this is the sun. So what is the amount of energy produced by the sun per second? So that is called luminosity. So if the total energy produced by sun within 1 second is one particular number of joules, so joules divided by seconds, so we get the watt. So that is about the total electromagnetic energy emitted by the sun. So that is called luminosity. So luminosity of the sun is approximately 3.8 times 10 to the power 26 watts. So it's a huge number. So that is one concept. The second concept we are talking about is the flux. Flux is all about light energy that comes through a 1 square meter kind of area. So if the sun is a circular object, if you go closer to the sun and check what is the amount of light that is passing through a 1 square meter area perpendicular to the sun, it is high. So if you go far away, because this is radiating out like that, the amount of light comes through a 1 square meter area is less. So although the luminosity is high, the light flux gets reduced as we move away from the light source. So flux is watts divided by square meters. So 1 square meter area, what is the amount of wattage that is passing? So that is all about flux of light. Okay, so those are very simple concepts. But there is a problem in measuring light in this way, because the luminosity and this flux we are talking is all about the total electromagnetic energy that comes out of an object. The problem is it is not important that it produces what is the amount of ultraviolet electromagnetic energy it produces, what is the amount of radio waves it produces. So that is not important. What is important for us is the amount of visible light emitted from a body that we can use to see. So this concept of joules divided by seconds doesn't work for us, because we are talking about only the visible spectrum of light. And in that spectrum also, as I explained earlier, you remember, we are sensitive more to few frequencies, and towards the edge of the spectrum, we are also less sensitive. So what is the amount of visible energy that is produced by a light source, and what is the amount of visible energy flux we see? So we need a separate concept. So this concept is not working for our purpose. So the visible light is not measured in joules, therefore. So there's a different unit for that, that is called lumens. Okay, so that is the difference between joules and lumens. Lumen represents only the visible light energy quantity. So that is lumens. So the study of light is getting complicated little by little. One is we are talking lumens, not joules anymore. Plus, there are several things we use when we consider lighting. So if there's a light source, let's say this is the light source, luminous flux the term luminous flux is the total energy that the light energy that's emitted by a light source. If there's a light bulb, the luminous flux is the total light energy, which is measured in lumens. But if you take a light source, it emits more lights towards one direction and no lights in the other direction. So if you take a usual torch you use, the torch emits lights in one direction and it doesn't emit lights backwards. So there is a reflector in the torch, so the reflector reflects all the light forward. So there's another parameter you use in lighting that is called luminous intensity. So luminous intensity refers to the light that comes through a one solid angle. So remember, it's not just a 2D angle, it's a 3D angle. So it is measured in steradians. So amount of light energy that comes through a one steradian angle is called the luminous intensity, okay, which is measured in candelas. So clearly understand this difference between lumens and candelas, the luminous flux and the luminous intensity. So this is related to angle. Okay. So light energy per solid angle is called the luminous intensity. The total light energy of a light source is called the lumens, the light energy output or the wattage kind of thing. Okay, luminous flux, luminous intensity. I think it's clear for you. Then we are talking about something else when it comes to lighting, that is illuminant. So we are, as designers, as people who create interiors, we are not worried about, ultimately we are not worried about what is the light fitting, what is the luminous intensity. What we need is the illuminance on the workplace, the amount of light that falls on a surface. So that is called illuminance. That is measured in a terms called lux. So this is lumens, this is lux. So amount of lumens that falls onto a 1 square meter area is called illuminance. So we have meters to measure illuminance and so forth. So we will discuss them in few minutes time. So that is called lux. So lumens per square meter is called lux. So that is the amount of energy fall on a surface. We do everything to get the proper lux level on our rooms. So lux is the ultimate measurement. This is the most important thing for us. So it is lumens divided by area, lux, okay? Then there's another concept you will find in lighting, which is not very important for us, that is called luminance. So this is illuminance, this is luminance. Luminance is how bright a surface appears to us. So although we have a bright light falling into this surface, if this surface is dark, it will appear to be not so luminant to our eyes. If this is a white surface, it will be very, very luminant for us. So it is how a surface appears when you look at it. So this is illuminance is about light falling onto the surface. Luminance is about light coming out of a surface. So it is measured in candelas. So candelas divided by square meters is called luminance. So flux or lumens divided by square meter is lux. The candelas divided by square meter is called luminance. So that is the difference. Okay. So just remember these concepts. These are very important in lighting: luminous flux, luminous intensity, illuminance, and luminance. So if you want, you can forget luminance. It's not very important. Just remember these three: luminous intensity and illuminance and luminous flux. Okay.
I have a question, sir.
Okay.
But we have measured all the building is illuminance, the lux level.
Okay.
Am I correct? But
Mostly, yes.
But the thing we are seeing is luminance, because the surface is getting the brightness or intensity amount of lux. but we are feeling is luminance.
Partially correct, but what we need light is to see things. So if it is your working table, the luminance of the table is not important. What is important is whatever the thing you put on the table, you must be able to see. So let's say you put whether the book you are putting on this, whether it is red or whether it is dark blue, whether it is black, is irrelevant. You can put different books on your table, but what is important is the amount of light that falls onto that and whether it is sufficient for you to clearly see that.
So even though that we can see from our eye, so
yes, let me explain. So if you take spaces for, let's say, working, let's say, for sewing, for computer works, for office work, what is important is illuminance. So that's why we have given more prominence to that one. But if you take a decorative, let's say, architectural space, let's say a wine shop. So when you enter into the wine shop, it is how you feel the shop, the shadows, the light, how it appears to your eye. So in that case, you have to look at the luminance. It's a more artful thing. So that is important. So when you paint your walls in a little darker color, the luminance of that space will be totally changed. So both are important actually.
I got it.
But in most of cases, so because I'm talking to an audience of engineers, the illuminance is the dominant thing. Okay. Right. Right. Good. So remember luminous flux, it's measured in lumens. And then luminous intensity is the other thing we discussed. So luminous intensity is something very important when you go to select light bulbs. So remember luminous intensity measured in candelas, it is about light energy per angle, per steradian angle. So when you buy a proper light fitting, they will give you a chart like this with that light fitting, which shows the distribution of luminous intensity of that light. So when you select a light, especially for sustainable lighting, get this chart and have a look at this chart. So this particular light fitting, you can see it emits a lot of light in this direction. So luminous intensity here is high. So this circle here, these circle lines, that shows the amount of candelas emitted in direction. So this is direction 180 degrees to 0. So this particular direction, this red line goes like that. It comes here. So that means about 200 candelas is emitted in this direction. Whereas if you look at this direction, 170 degrees, it's only 40 candelas. So this graph shows the luminous intensity. So this luminous intensity graph is available for any light fitting, any means quality light fitting. So you have to look at that when you select light fittings. Okay. Calculations may not be very important, but to understand this concept of candelas and the luminous intensity is important. And then we are talking about polar luminous intensity graph. That is because the light fittings are not perfectly round. So we get this kind of long light fitting. So we have one distribution in this direction, another distribution in this direction. And then several other directions you can take different light intensity distributions. So usually in these graphs, you see two graphs like this one and this one. One is horizontal direction and this is the perpendicular to that one. So don't be confused why two things are there. So next time when you go to practice, take these luminous intensity graphs of light fittings and then study them. So you will see two, because one is perpendicular to the other. So two directions they have taken like this. Actually, these polar luminous intensity graphs, nowadays we are not talking about these 2D graphs, although as tradition they give it. We nowadays give a 3D graph like this. So that shows the distribution of luminous intensity 3-dimensionally in all directions. So in a particular light bulb, this is the 3D luminous intensity distribution. And actually, this is also not important these days. Right now, what happens is when we select light fittings for interior lighting, what we do is we ask the lighting manufacturer to give us the .ies file. IES stands for Illumination Engineers Society, I suppose. So there's a file called .ies, which gives the light intensity distribution of the light fitting they have created. So when you ask to send a .ies files, any lighting manufacturer gives you the IES files. Then I think in any simulation software, you can use that file and then see how the light intensity works. So we can do it in Blender also. I have sent you some .ies files for your reference. So after the break, we will look at how to do it in Blender. So this is some of the IES files I have used, and you can see how these light fittings emit light. Okay, so that is about luminous intensity of light fittings. And about illuminance, in Blender also you can simulate, you can use that IES file and then simulate the lighting of an interior and then get a graph like this, but you have to use a plugin. So because it is a little bit advanced, I'm not going to teach you. Because this is a little bit advancing, I'm not going to teach you how to do it, but I will give you guidelines how to download the plugins and how to do it. So if you are interested, you can do it by yourself. So what this graph shows, for example, if you look at this graph, the different colors doesn't show colors. What they show is the amount of lux, the illuminance on the surface. So this bright color means it's highly illuminated, about 378 lux. So this towards this blue region, it's about 9.7 kind of thing. So you can see less illumination here, high illumination somewhere there. So with this simulation, you can actually calculate and see whether the amount of illumination is sufficient or not before construction. When it comes to large scale projects, what happens is we provide the 3D model to the lighting manufacturer and he runs this simulation for us in different softwares. So there are softwares you can download and do it also, but in Blender also you can do it. Just ask them to supply the .ies files, put them on light fittings, assign that, and then you can run this. Okay. So these are the lighting levels. So this is the meter we use to measure lighting levels. Nowadays you can do it on phones, but it's not so accurate. So you have to use a meter like this. And when you measure the illumination level, you have to find out whether it is sufficient for that particular space. So the sustainable way of designing lighting is you provide the exact requirement. You don't provide lighting more than what is required, which is a waste of energy. So let's see some of these lighting levels. This one for drawing officers, chain stores, general electronics work. So that kind of a space require luminous intensity, the illuminance of 750 lux. So for drafting works, supermarkets, we need about 1000 lux. But for precision works like hand tailoring, precision assembly, detailed drafting kind of things, we need a very high lighting level, about 1500 to 2000 lux. For, let's say, libraries, sports assembly halls, lecture rooms, so it's important, the lecture theaters, 300 lux is sufficient. For parking lots, it's about 100 to 150 lux. So these are the standard norms. I will give this lecture note so you can use this. So when you are doing lighting design, first is get these numbers in the simulation and then reduce the number of light fittings used, and then check the space with the light meter and make sure that the requirement is achieved. That is how to do sustainable lighting. And then in lighting, there is another concept very important, that is the efficiency of light fittings. When it comes to efficiency, once again, that problems comes to us. The total electromagnetic energy output of a light fitting versus the amount of visible light output. So what is important to us is not the total electromagnetic energy output. What is important to us is the amount of visible light emission of a light fitting. So we have given the word efficiency for the scientists to use to determine the total electromagnetic radiation, and we are using a different term called efficacy, which is symbolized by this eta. So efficacy is not the total electromagnetic energy output, it is about lumens. So let's say we give 100 watts to a light bulb, then we check what is the lumen output of that light bulb, and when you divide the lumen output by the wattage, we get the efficacy of the light fitting. Okay, so that is called efficacy. It's a very important concept. So these are the efficacies of different light sources. It's a comparison. For example, LED light usually have 180 lumens per watt. So it's a very efficient kind of light. So the sodium vapor low pressure lamps we discussed, they have also 180 lumens. So they are as efficient as LED bulbs and they are much cheap. But the problem, as we discussed, is you understand it is their color rendering index is very low. Sodium vapor lights. So wherever you can use the sustainable way of doing it is look at the color rendering index, look at the function of the space, and then see whether we can use these lights. So if possible, you can go for them. The sodium vapor high pressure lamps have about 130 lumens per watt. The best ones, the incandescent lamps, the problem is they have a very, very low efficacy. It's only 20 lumens per watt. The halogen lamps have a little better performance, 30 lumens per watt. And mercury vapor high pressure lamps have about 58 lumens per watt. So we have the table here. So I'm just leaving it with you. So refer to that. So use these tables you needed to remember things, but you should have a general understanding how things are. And you have to use this knowledge when you are selecting light fittings. So if you understand the fundamentals, you can do it in a sustainable manner. Okay, so that is all about what you should know about artificial lighting. One important thing you should know about exterior lighting is the light pollution. It is something important you should notice when it comes to sustainable lighting. That the dark sky is something very important. So when you emit too much light into the sky, it is a disturbance to the flying animals like bats and then other insect creatures. So it destroys them. It destroys their life cycle and so forth. So using this kind of light is very bad. Always try to do design light like this when you do outdoor lighting. So in the green rating system, if you avoid light pollution, I think you are given 1 mark. So look at that table. So that is there. So always use light only where it is required, and make arrangements that lights are switched off whenever it is not necessary. And then avoid light pollution as much as possible. Okay, so that is all about lighting. So we will take a half an hour's break, and then we will look at the blender, how to do this kind of .is file using, and then light up a space using blender. So I think the IES files I have sent is in your WhatsApp message. So just download them, load blender, and get ready. Okay, so we'll have a small break about now it is 10:35, 10:50 we'll get back. Okay.
Okay.
Okay, I think everybody is back now, isn't it?
Yes, sir.
Okay, so what we'll do is then I will quickly explain how to do that lighting simulation. So you can also open Blender with me. What I'll do is I will, for the time being, delete all lights and everything. And I will create first a small platform for me to put things on. Then I will create a back wall like this. So I can see the light distribution there. Okay. You also can do that. Then what I will do is I will add a light here. So you can reuse the light that was there if you want. Otherwise, you can add a new light. Go to add light and any light. I'll take a point light. And I will move it up. And I will move it close to the wall like this. I think a bit more closer like this. I'll move it there. Okay. So this is my light, and for me to see how this light lights up a thing, I will create a sphere. UV sphere is also, icosphere is also. I'll select icosphere. Any object you can use, if you want, you can use a cone. So this is the sphere. I think it's little too big. I will scale it down. This size is good for me. Okay. So I'm going to look at how this light is going to light up this object. So can you all create this? So once you finish it, just tell me.
Finish.
Okay, great. So I assume others are finished. So is it so?
Yes.
Okay, so everybody has done it. Okay, so what I'll do is now I will select this light fitting. Okay, and I think it is better we will first go to the rendering menu, then we will see the difference that what is happening. So in this one, in this panel, I'm going to click this viewport shading. So that shows how this light fitting has started to emit light. So if you select this one, it has only very small amount of light. So what I'll do is, for the time being, I will just go to this light panel. I will increase its power from 10 watt to 100 watt. Yeah, just for the time being. So it's like it lights up the space. Okay, so this is how this light lights up. So it's just a light now, nothing else, just a point light. And to see a proper lighting simulation, I'm going to change my rendering engine. So you remember how we did that? We went to the render properties tab here, this one, render properties tab, you remember that? And then I'll put this somewhere there. In the render properties tab, the render engine, we are going to change it to cycles, which is a proper light simulating engine than EV. We change it to cycles, you will see a proper light tracing based simulation of lighting. So this is that lighting system. But there are some dots going on there. To avoid that and get a smoother view, I'm going to click this denoise button.
Excuse me, once a time, can you tell how made it black, dark?
Sorry?
How it made as dark? Once a time, can you tell me, sir?
How to make the entire thing dark?
Yeah.
Background?
I missed that.
Can you do it once again? Please?
Yeah, okay. I think if you go to this viewport shading tab.
Okay.
Yeah, when you go that, the light that comes on these surfaces will be the exact simulation, but you're asking how to make this background dark.
Also, just the cubes are all are made dark. That means what is the selection, I thought?
Your cubes are looking very, very dark.
My cubes are just previous sessions we follow that ash color like that. No, sir. They become dark. That's why I'm asking how it make it.
We change the default color of the cubes.
Okay.
I think it has nothing to do with. No, in this one I can see. I mean, if it is this particular tab we are talking about, in this one, we can go to this studio here, and here we can change it.
Okay, so.
But in the rendering tab, This is a lighting simulation, so it doesn't affect anything. So it should come here. If it is not coming, you just for the time being click this light, go to this light, then increase the power.
Okay.
For the time being, just increase the power. So I think now everybody has done this, isn't it? So what I did was just select the light. Then here I change this into the rendering mode. Went to this rendering properties tab and change the render engine to cycles. Then in that one, I added denoise here. Switch this on. That's all. Yeah, I hope everybody has done it. Then what I'm going to do is I'm going to add this shader arrangement here for the light. Right. So what I'm going to do is here you can see there's a slider here about this is a time slider. I'll just drag this up. And if I'm going to click this corner, this button here, so I can change what is displayed in this window. I'll click this and I'm going to select shader editor. Just click this shader editor. So this window changes into a shader editor like this. Any window you can change into anyone, even this 3D view thing, you can click here. We are in the 3D viewport, so you can change it to, there are many other views, so you can change to anything. So we will for the time being stay there. Okay, has everybody done it? Can Dunstan do that?
Yes.
Is it? Yeah,
Yes.
done. Okay, okay. Ruan, have you completed it?
I have done.
You have completed. Okay, right. So then what we'll do is select the light fitting and go to this object data properties here, this light fitting thing. Click that on. And then there is a button called nodes. So click use nodes. Just click this one, use nodes. And then on this shader editor thing, this kind of node arrangement is there. So this is a visual programming language. So this is the way many things work today in this industry. So we have equations or parameters, and we are connected them with kind of these wires called noodles. So these are nodes, these are noodles. When you connect this here, something happens. So this is light output and this is the emission. So emission has 2 sockets to connect, the color and the strength. So first you come here and then we will discuss. Just come here and then tell me. Okay, can everybody do it? So there's no issue, I suppose.
Yes, sir.
Okay, right. Then what we'll do is we have to connect another node to this color. So we were talking about black body. So the way to do it is you can go to add menu here, and you can click search button here and then click black body. It brings you the black body thing. Click there and select. Otherwise, you can go to add converter. Black body is there. Just select this black body node, bring it somewhere here. Click, then it will stay there. It says temperature 1500. It's a color thing, so just drag this thing, click and drag, and connect it into this color. Now this 1500 temperature is applied to this light fitting. So what you see is that color. Okay, once you complete, just tell me.
Yes, sir.
Okay, great. Then what I'm going to do is I will select this light fitting and this object. I will copy one time, because then I can see different colors. What I'll do is I will press how to copy, Shift D. Yeah, Shift D. Then I'm going to give the direction. I think it is Y direction. No, it's X direction. I'll press X. We'll move it a little bit here. Place it here. I will use Shift R to repeat the same thing. Shift R and Shift R. So I have 4. I will try out a different color for this light fitting. I will select this one. Then here is my node tree. I will, instead of 1500, I will put 5500. So then this is the color. This one I like to put 15,000 Kelvin. It's a bluish light. This one I will put 6,000. I think I will put 3,000. Okay. Okay, I think everybody can do it, so you can experiment with it later. So what I'm going to do is I will bring in the IES file and then see how different IES files distribute light. So I'm going to select one light fitting. So this light fitting, let's say, and I'm going to add another node. It's a texture node, texture. I will select IES texture. So it's like this, add texture or IES texture. So it will give a node. So just bring it wherever you want, click it. That node is there now. If you can't find it, just search IES. It gives IES texture. Okay, so when you find the IES texture, click external button here. There's internal, that means built-in IES textures are there. We'll click external button here, and then a folder appears here. Can you see that? When I click external button, a folder appears here. Just click that folder button, and then select the IES file. We saved it here. So I will select this side. I'll select the first one, this one, and I'll select it and say accept. And nothing happens because we haven't connected this to the correct socket. So this IES file has a socket here. Drag this socket and connect it into the strength here. All right. So that now this is how that particular light emits the light. I think to get a clear picture, we will move this, my light fittings, I will move it a little closer to the backward, and we will get a proper view, I suppose. Let me move it. Furthermore. Let it render. Okay, so we will experiment with other lights as well. So I will select the second light, this one. So it doesn't have this thing. I will go to add, search this time, IES. There's IES texture, click it here. I will select the second light, go to external, click this one. I will select the second light, this one, accept, connect. That is how that light works. So I'll keep on connecting. You can also do that. Select the light and then we will add texture, IES texture, external, third one. Fourth one. Okay, so likewise, you can simulate the light and then see whether you get sufficient light, what is the ambience you get out of these lights, what are the temperatures you can use, and you can very correctly simulate them and then come to conclusion. So this is the best way to design sustainable lighting. So you reduce the cost of light fittings, reduce the energy usage by the virtue of exact simulation of the lighting distribution using .ies files. Then virtually you can measure the lighting levels that is given out, but we are not going to do that because it is a little bit complicated. The system is called VI Suit, so it's a plugin. So I don't know whether I'm going to use it in the coming weeks. So if we are going to use it for something else, we will see how to do it also. So with the VI Suit plugin, you can exactly calculate the amount of light that falls onto different surfaces. Then with that, you can decide how to reduce the lights you are using, how to reduce the energy usage for lighting, and then do sustainable lighting. Okay, so any other thing to ask? Can everybody do it without a problem?
Mhm.
Yeah.
For me, it's a little bit different. Shall I share my screen?
Of course, of course, of course. Ah, right. But it's beautiful. Right. So the difference is, I think your objects are a little bit bigger than the ones I have modeled. So that's why it's little different. And light fittings are a little bit closer. Other than that, I think everything is right. So you have done it correctly. It's so beautiful.
Okay, sir. Thank you.
Right. So is anyone else who would like to show? Mahesh, can you also show?
No, sir.
Okay, right. Anyway, you can give a try later. Right, so it's a very interesting thing to do, very fun thing. So try it out. So if you model your house and simulate lighting, it will be fun for you also. So try to use that tool. It's a very easy tool, but it simulates pretty much exactly the lighting distribution. Okay, so what I'll do is then we will, because we have few more presentations, we will give opportunity for Faisal to start.
Okay, sir, I'll share my screen.
Right, okay.
Good morning, everybody. Today, my presentation depends on sustainable construction based on site context. I selected the site at New Orleans City for a stadium. New Orleans City is a beautiful city with the tea hills of central province of Sri Lanka. The city is developed in most tracks, especially with tourism industry. New Orleans city has commercial buildings and a lot of hotels and high community area. So my site selection is near the Gregory Lake and surrounding tea plantation. Site located at the top of hill tea estate and beautiful access road with a slope terrain, and land geographical view is shown below. The land terrain shape is this. My site selected area shown in this is the portion, the hilltop. And site condition is easy for access from city. The site has a slope area and it faces to Gregory Lake, surrounded with the tea plantation. No buildings surroundings in 500 meter radius. Rainwater catchment slopes to Gregory Lake side, and site located at the top of the hill. My proposed stadium view is this. I designed for with the sustainable concepts, and I applied the stadiums, just the wings through surrounding area with solar panels to target sun coverage whole time, and also stud columns to balance the minimize vegetation clearance. So only stud columns and top of that stadium will build up, and also the hill top of the hill used selected for balancing the cut and fill to minimize the earth haulage. And this is the round area coverage with the solar panels, and the sun path and applying the designing common wave of on sun on top, and also shadow effects of the building from a side view.
Okay.
This is my presentation. Thank you, sir.
Okay, right. So then there's, I think, two more who wanted to present. So I don't know whether they are ready.
Yeah, can I go next, sir?
Of course, Madhavi. Yeah.
So I have a power cut, so Mahesh will be sharing the screen.
All right. Okay. Right.
Thank you, Mahesh. Okay.
Yeah, we can see the screen.
Okay. Good morning, all. I'm Vijayasekara DMP. First of all, this is the site I have selected specifically in Anuradhapura, Oyamadu area. Why I select this particular location is in 2012, the Kirula was, which is a national development exhibition, was held in this area. And now it is a barren land and no use of that, and no any other structures there. So before that, the government has totally developed this area in terms of road facilities. Oyamadu is 29 kilometers away from Anuradhapura, but it is road facilities. I believe that it won't take much of time, because that it is not that of a crowded area, and also that no any natural disasters have recorded in that area, and also we don't need to do much of the developments or modifications to the land, because Anuradhapura is a very flat land area, and also there we have a very less rainfall. That's why I selected this site. Moving to next slide. Maheshi, next slide. Okay. No, please.
No. Up. One, two up. That one.
Okay, thank you. When I am doing the design, it's okay, thank you. When I'm doing the design, I refer to buildings. One is Colosseum, which is in Rome, and also this Nelum Pakuna. And I just can't get an alien design and plant it here in Anuradhapura. So I decided to give that the cultural touch to the building. So that seat arrangement is done, inspired from the Nelumpakuna, and also the roof of the building is, I have inspired from the lotus petals, so that the top view is also there, which is like a flower from the top view, and the square is the parking area that I have chosen. Next slide. This is the design. So this square part is the parking area, and the building is there. So you can see that I have inspired from the Colosseum. So those it is like a cylinder, and those squares are cut away. And from the top view, it is like a flower, and it's like I have taken the I have inspired from the lotus flower, so that I took like shapes like a lotus petal. Moving to the next slide. When I am building this one, Anuradhapura is a really hot area. So that if I can give the natural ventilation, HVAC cost can be deducted. So from these open spaces, ventilation can get. And also this is from the top view. When I look at the top view, the ground area is open. So there is a less rainfall in Anuradhapura. So it won't be that much affected when we are using the building. And also, since it is a very sunny area, from the top of this group, solar panels can be installed. In that way, lighting also natural lighting, and solar panels can be installed, and also natural ventilation is also assured. So moving to the next slide. This is the sun path North has shown. You can see that this is a barren land area, and also when I'm doing this topography part, although I apply buildings, I couldn't see any differences. So I use that highway thing as well. Moving to the next slide. I have selected 2 months,
Okay.
July and December. So you can see that 9 AM July, how the sun angles are shown, and also the December 9 AM and 4 PM. So 2 months are taken and compared.
Right.
Next slide. This is the shadow analysis. That I have a benefit that there are no big structures or the houses or any other structures in this land. So the shadow casting would not be a problem for other buildings. And moving to the next one. For the recommendation, when I see that when I have applied this sun path, I saw that the seated arrangement will be affected due to the sun. So I have decided propose this the modification to be done. If you can zoom this, you can see that. But I didn't add it because it damaged the aesthetic.
No, it's okay. It's okay. Now, most important thing is you identify that direct sunlight is falling onto the seating area. Then some modification has to be done. That is the most important thing. So you have done it.
Okay. Thank you so much. That's all.
Right. Okay. Right. Okay. That's good. So that is the most important thing. When you model, you identify that there's direct sunlight falling through windows, or maybe if it is a seating area, it falls exactly like this on the seating area. Then some modification has to be done. Then the second step is easy to do the modification and then come up with the solution. Okay. So that is what is expected. So it is done. Okay, great. So I think there's one more person to present, isn't it? Yeah, I think is he absent today or what?
I think so, Narendran.
Narendran, yeah.
Fix. Last time he just replied that he's having fever or something.
Yeah. So Narendran is absent today, isn't it? Yeah. Okay. Yeah. Okay. So that is okay. So then what we will do is, I think some of you have tried to work with this sun path thing. So I will give opportunity to one by one. So those who have done it can just show it. So we have seen the Madhavi's one and then Faisal's one. So if Dunstan has tried something, then you can just show us.
Yes, sir.
Okay.
So it's visible?
Yes.
Yes. So this is the location I have taken the coordinates.
Okay.
And this is the second screen is visible, sir?
You have to click, I suppose. We are seeing slide number 14. All right, 15. Okay.
Because when I make it full screen, the slideshow, but it won't loop. So
it doesn't happen. Yeah, it's okay.
So this is the second one. I have taken the sunlight on 24th 3rd. It's I have taken the 12 hours and check whether it's looping. So it's initially this area it's highlighted, and around 6:14 it's little light up on the stadia.
Okay.
So this is the time I have taken, and at 6:15, I can see the most shadow on the backside of this area, and this is the rest of the time. So then sun comes up, the shadow is going to be reduced, and when it's reached around 2 o'clock, the building, it's almost the sun is on top of this one, because the orientation of this building, it's exactly on the east and west, the sun direction path, little bit tilted. So the morning time, the whole sun comes inside, and the evening time also the same thing is happening in the stadium, because it's open one. Right. And the evening time we have the most shadows on the road area, and half of the pond is covered with the shadow. Okay. Finally, I'll get the stadium is oriented along with the east-west direction, slightly angled, and morning and evening hours sun directed to the stadium. It's an open pavilion, so there is no any issue depending on the Norelia climate. It's very low temperature, so it's better we have this sunlight comes in. Right. Evening hours, the building shadow casted along with the road and covered half of the pond. So this is the thing. Actually, I have made it for the first one, but the second one I did some little more detail. Okay. This is my the location. And this is the sun path. It's from morning 6 a.m. to the afternoon, how it's goes along the site. Okay, so this is the second afternoon, 1 o'clock, 2, 3, 4, 5, 6. And this is the same thing I have did from the morning 6 to how the suns pass over the site. And this one actually, my site is it's located, oriented along the north to south. So the sun is come from the perpendicular direction. So we have more details. So when I see the shadow, almost this area, it's covered with the shadows. And for a day, and this is the afternoon time. So after 4 o'clock only, I can, after 3 o'clock only, the shadow is reduced this area, and nearly the 5 o'clock, I have the sunshine in this area. So initially, I have designed to extend this one, both sides, as the shaded portion, shade. But after that, I think this is more I have projected. So then I reduce this one little bit. Okay. You see the front elevation, already I have the opening, the door is there. But when it comes to 2 o'clock, the sun hits on the door area. So here I introduced the shade. So when I try to introduce the shade, first I make a small rectangular shade. But when it's reached to the 4 o'clock, so again the sunshine goes inside. So then I will drop on the top. So finally I get the design of like this to cover this area. So this is the structure I have introduced on the front, and I reduce this one. So then I analyze the whole year. The January, it's like this, the same day. February, March, April, and April, and then May, June, July, and I have the critical one is July and August. So then it's a little bit okay the rest of the months. Right. So finally, I got the design like this. So I reduced this area little bit, and I have introduced on the front area for the shading. So finally, this is my design. Right. So this is the thing I have finished from this one. Right. So great work. Very nice. So that is the most important thing. So with this software, without much of a calculation, you can design the shading devices you require. So if I once again share my screen. Sorry. If I share my screen, let me go to the presentation. Yeah. So for example, this building I have shown you earlier. So this is exactly designed in that manner. So like Dunstan has done. So this small shading device, this way, and this big shading device, it's like the shading device he has designed. So there are a lot of direct sunlight coming in. So we have windows. So there's no other way. This is the way to cover it. So good work. So this
This is a constructed building. We completed this 2015. I think it's in operation for 7 years now in Kandy. So that is how practical works can be done with this system. Okay. Right. So then that is tungsten. Okay. Then we will move on to Ruan. Is it Ruan?
So, okay, I'll share my screen now.
Okay.
Can you see my slides?
Yes.
Okay. Okay. Good morning to everyone. So this is the second part of my stadium design project, the sun path analysis. So the orientation of this building, with this blender model, I can see that sun path is I arranged my building in the correct manner without knowing that actually.
Everyone can do PowerPoint simulations very nicely. Yeah? So that sun movement is very nice.
In this direction, thank you, sir. And this direction, I think it's a correct way to arrange the building. So, so I identified the extreme sun angles occurred in around December and June. So this is the 8 a.m. Shadow casting. This is the 12 p.m. and this is 4 p.m. What will be the shadows casting on the nearby buildings. So I did further analysis like what will be the morning and evening shadows on this building in each month. So I created this image. This is for 8 a.m. and this for 4 p.m. What will be the in each month, like what will be the shadows. So I identified which areas will be the affected by these shadows. So basically these two areas. So these two are areas. I think most of these are residential buildings. I think there will be not much effect on this building. Right. So in other case, I identified that in May and August, the front entrance area of the building, this area is not covered during the sun due to sun angle, and other months it's covered. This midday, like 12 p.m. shadow. So I've used this and modified my roof to extend up to certain area level that can cover this front entrance area. So that in those months also they can get some shading. Okay. So this is my sun path analysis. Thank you very much.
Right. Okay. So good work. Very good work.
He did the video. It's really impressive.
Yes, really impressive.
Yeah,
yes.
I'm also
Nice.
thinking that one, but I cannot. I couldn't make it that one.
Right. So Ruan can explain others how to do it.
Yeah. So that can I did was I take change the month and take a screenshot in same orientation. I took several photos and using a video editor I lay all together and make a video.
Okay, so you have done a lot of work.
A lot of software he used.
But no, you can actually animate.
Like using a Windows Photos app, you can do it.
You can do
Windows
it, but
Media.
yes, but it's not required. Ruan, you can do it in Blender itself. You can animate. You can do the entire animation and you can render animation.
As well, sir?
Yes.
Okay.
Actually, in Blender, you can do entire films, including video editing. So there's a video editing part as well. So that is why it's called Blender. Everything is there. So the way you have done is very impressive. So it's very nice. But look at that also. I am not going to teach you how to do animations, the timeline and so forth. But you remember the timeline we lifted up and change it to the shade editor. That timeline is there for you to do animation. So you can put keyframes there, run animations. There are systems of rendering things and then saving it as video files, AVI and so forth. So everything is there so for you to explore. Anyway, great work.
Thank you, sir.
Right. Then shall we look at Madhavi? Can you show something?
I did, sir.
Sorry, not Madhavi, Maheshi. Madhavi
Yes,
is done, yes, sorry. Both are starting with late time, I just messed up.
sun shining in. Can you hear me, sir?
Yes, your voice is a little bit breaking, but we can hear you. Yes.
Sun shining into a building provides free heat and natural light, but it can also create glare when the heat when it is not needed. Discomfort and added demand for cooling, using sunlight when it's needed, deflecting its power when it's not, are two of the most important tasks we should do when we are designing a building. So we all know the sun rises from the east and sets from the west. Because of the Earth's rotation and its axis is a little bit tilted, we don't get the sun exactly in the west or east in every single day of the year. Sometimes it rises north of the east and sets north of the west, and some months it sets from the south of east and rises from south of east. The height actually depends on how far we are from the equator. So in my design, the slots I've kept here have for ventilation have made this design a bit more impractical because the sunlight falls directly through those, and so I've had to do some modifications for my design. And I'll show now why I need to do my modifications, because on the month of January, as you can see, this area of the seating area would be illuminated, would be cast direct sunlight, and this area would be under direct sunlight in July. And you can see the slots have made it impossible for the people to enjoy a game or some sort of something like that in the month July, September, December, and this is also in December. And afterwards, I've created this sort of hat sort of thing because all the slots would be covered by this, but the ventilation would also be there. But we would need artificial lighting for this. And I've checked during all 6 months of the year, in June, July, August, and in September, October, December. And this is what I've done from the Blender parts you have taught last week, sir, but I didn't exactly do that much as the others. And this is what I've done. Thank you.
No, but this is sufficient. So you have you have used the software, you know how to simulate things, and then this particular oval shape shows the sun path itself. So where you need higher shading, you have make it come out more, and then the other directions little. So you have done sufficient work. So this is okay. This is good.
Thank you, sir.
Right. Then Faisal, we looked at his work. Prasad has sent a message that he's at the site, so he can't do the presentation.
So I have his presentation if you want
Yeah,
to see.
of course. If Prasad is unable to talk, then you can present. It's okay. So these slides we saw last time. Yeah, from there, I suppose. Yeah.
And sunpath, by analyzing the impact of sun on site as well as the building's location, the spatial arrangement, orientation, window placement, and daylight access and other design features, the designer takes full advantage of passive solar design features and increases the energy efficiency, comfort, and financial value of a building. And when assessing a site for sun, we consider the time during the day that the site receives sunlight, the sun's path at different times of the day and the year, how the site shape, slope, and orientation affect the solar excess, how obstructions such as adjacent buildings, trees, and landforms will impact on the site and the potential design, the owner's lifestyle, for example, when they want sun or shade. He has done sun path analysis. The stadium is facing northeast. It would be better to face north or south to avoid direct sunlight into the building. he has shown that the how direct sun hits on the month of April here.
Yeah, it's, I think, a beautiful rendering, isn't it? Very
Yes.
nice shadows.
And he has shown again on because of the view proposed design cannot be turned to corrected design directions. As a solution, roof of the stadium could be fully covered to avoid the direct sunlight into the building.
Okay.
And sunlight affects the durability of many materials. Colors fade. Plastic-based materials may become brittle. Timber moves and twists, and expansion and contraction from heating and cooling places stress on many materials. Impact of the HVAC system. So the effect of UV radiation over building lifetime must be considered if they're being affected direct sunlight. And that's it. Sir. Thank you.
Right.
And he
Okay.
hasn't made any design corrections because he has stated that we can put something over the stadium roof to give some sort of shade.
Yes.
But other than that, there's nothing he needs to correct. I think there's nothing.
Yes, and but even that one, if you go to the previous slide, yeah, that one, what he refers is down there. Yeah, exactly. So there are some strip of light comes in, so it is better to add some shading over that. But even if you don't do that, that few strips is fine. So you can leave it that. So we need some amount of sunlight also. So it's nice.
I'll pass
Yeah,
that answer. Thank you.
Yeah, right. Okay, right. So I think then Taraka, I think we'll present next time, isn't it? Taraka, have you done something?
Yes, sir. Now I have power cuts.
Right. Okay. So Taraka and Narendran can do next time.
Okay.
Basically, I think we have come to the end of today's discussion. So what you do is,
I have a question. This is
yes,
not about the lesson. This is the issue that I face in factory. Usually I am doing this accident investigation. So I have found within these 3 months, there are more than 10 accidents related to staircases. So I have a doubt there is a problem with the standards or the measurements of the staircase. I have the measurements, but not right now. Sir, is there any standard specifically to the industrial building staircases? I searched, and one of my friends sent me that it is to the office building and the public buildings and all, but the staircase in my factory, it is more a private staircase, like a home staircase. The measurements are like that. So I need to give a solution for that as well. I need that industrial,
Madhavi, there is no such standard called staircases for industrial as such, but there's general specification only. But even if you follow the general staircase design requirements, I don't think there's any room for any kind of, let me share the screen if possible. I will share screen. I'll try to draw something somewhere. I'll go to this slide. Yeah, give me 1 second. I will try to draw. Usually, so if I draw a step, these are the requirements. So this thread, this one minimum is I think 154. This is the.
I think it's not satisfied.
It is not satisfied. That is one reason, and then this one must be the maximum should be 175. So if you go beyond these, staircases are not safe. But the proper practice is you make this 154 is also very small.
Because they wear that safety boots and also that staircase.
Sorry. Yeah. Sorry, this is not 170. This is 255, suppose. 255. This is 175. Best practice is keep this 150 and then make this 300. So that is the way we design. And then the biggest mistake people do is you select wrong material here. So if your material here is slippery, you have to have anti-slip arrangement here. So if not having that is the greatest thing. So what you have to do is usually if it is tiles, you have
it's cement, sir. Factory, it's cement.
Cement. Okay. Then it is compulsory. You have there's strips, anti-slip staircase strips. You have to paste on this. So those strips are available to paste, but in factories in Singapore like locations, what I have seen is there are some stainless steel knobs like this. If it was section, it is kind of a nail kind of a thing. The surface is rough. So if this is a staircase, let's say this is the landing. So you have to keep those knobs like this on the tip, so people will not slip. So not having this and anti-slip strip is the issue, I suppose. So if you
Sir, anything about the angle?
Staircase angle will be decided by this factor, no?
This
So
too.
150 by 300. So if you follow this standard, nothing will happen. So publicly used standard staircase, this is the angle we recommend. And also make sure the number of steps in a continuous one without a landing, this number, make it always less than 10. Otherwise, if somebody falls from here, he will fall a very long distance. And the other thing is in the landing, people do things like that. So that is also, you divide the landing like that, you have seen. Yeah. So if you are dividing it, at least keep one landing like this. So if somebody falls, he doesn't continuously roll over. So there's a place to stop. So those are the things you have to consider when you're designing a factory. And railing also is something important. So, the railing height and also in a staircase, 1.2 meter height is required. Usually balcony rail is 900, so most people use 900 high railing. So that is also causing injuries.
Okay.
Right.
Thank you so much, sir.
Okay. There's another chat that has gone. Yeah, there's a question from Faisal. When we zooming sometime, it will not go beyond that, it just slowly move. How to overcome this? Okay, so I will share the screen. Yeah, I think I have shared the screen. I will get out of this mode for a time being. Go to this mode. Yeah. Okay, I think Faisal, your question is when you
sometimes because
I understand. So when you have, let's say, some big object here, kind of a thing, sometimes what will happen is you keep on zooming, it goes very slow, isn't it?
Yeah.
So the way to avoid that is you click an object in your field of view where you want to zoom in, and in your number pad there is dot. There is after 0 there's this dot sign. Just click the dot, it will zoom into that, and after that it's once again smooth. Just try it out.
Okay, sir.
There's some problem with the coordinate system there, so you can break it off with that. So always press dot button and then it is okay. I think another problem most of you will face is when you start zooming in, especially when you do this GIS thing, when you zoom in, things start clipping, isn't it? I think Dunstan asked that question last time.
Yeah. That's why my search in video, I didn't got that. I heard that there's a shortcut key, but I didn't got that. That's why I'm asking.
Same thing. I'm also next prepared to share my screen. When I
right. Yeah. Okay. You can share. You can share. Dunstan. Yeah. I'll stop. Yeah. Yeah, now we can't hear your voice, Dunstan, but you can see. Yeah, that clipping problem. Okay. So what I have to do is press number N. In the keypad, press N. We can't hear you now. We can't hear you. I think you can hear me. Just if you can press number N on your keypad, then we can get the side panel. Yeah, there. Yes. Okay, then go to view menu. In that one, there's clip start, isn't it? It says 100 meters. Second one, reduce it to 1 meter. Yeah, now your problem is solved, isn't it? Okay. Yeah.
Okay, sir. Yeah, I saw.
Right. Okay. So we were unable to hear you while your video is on. I think
because the internet is a little bit.
Right. So I think that is the problem you had.
That's a problem. Yeah, that's the problem I face, because when I zoom to near to do some edit works, I cannot do that. Okay. Yeah. Thank you.
Right. So you can ask any other question like that, like Madhavi asked. So any problem you have, you can ask. So if I can, we can discuss that is working together. So we have time for one more question.
Excuse me, sir. Hello?
Yeah. Yes.
Okay. Because we are talking about this shadow generation. So I saw that in Colombo there are a lot of high-rise buildings constructed very close by. So because of this, some sides of the building will not get any sunlight.
Yes.
Is there any legal restriction so that we
have
follow?
Yes, the legal restriction we have right now is between building and the boundary wall, we have to have 6 meter distance. So when two buildings are together, there's about 12 meter distance. Earlier, we had regulations called light angle regulations. But when we want a proper density of a city, we have to do away with that regulation. So most of the countries, it is not followed. So you have to remove it. So that regulation is now no more. There's no light angle regulation as such. So earlier, you have to draw a light angle line. I think the angle was about 75 degrees. So that when you draw a line 75 degree angle, it cannot enter into other people's land. So that regulation, when you bring that kind of regulation, the problem is the density of the city we can't achieve. So we are talking about those things when it comes to city planning in your second semester, sustainable city planning. So we will discuss it at that time. Okay. So there is a little problem. But in a way, it is a good thing, I suppose, because in Colombo, what we need is the diffuse sunlight, and also we need shading, we need shadow. So we don't need direct sunlight falling into our buildings. So in a way, that is good. But if it is covering too much, then it is bad. Yes.
That I got the issue that when I see the buildings in the Colombo area, So I got this issue.
Yeah,
There will be an
yes.
issue. I think that's a good thing in another way, that it will be advantage.
Yes, there are advantages, but when you have two buildings together, we are going to discuss the building envelope next time. So when there are two buildings together, the problem is it traps heat inside. So if there's direct sunlight falling, it keeps on reflecting on these surfaces, and then total thermal energy is trapped inside the city. It is not emitted back to the sky. So because of that, the temperature of the entire city increases. So that is called urban heat island effect. So we'll discuss that next time when we come to the building envelope. So that is another part that is we have to discuss within this course.
You're right. Thank you, sir.
All right. So any other questions you can raise? It's 12, but we can, if you have another question, we can take it up. Okay, so I think some of you doesn't have electricity today, but I think recording of this lecture, I think Ruan will share with you. Then look at the recording and then study that lighting part. So that is something important. And it is important that you do these assignments we give, because the way we mark you at the end of the course examination is we will give 50% marks for the exam, and then 50% marks for the final assignment. But sometimes what we find is some of you do some mess up in the examination, then we see some people failing. So in order to avoid that, what we'll do is sometimes we get all these marks you collect for other sub assignments like this, and then we will moderate your marks based on that. So if you do these assignments, we can help, we can find a way to pass you if there's any issue with passing you out. So therefore it is important to do these assignments and then score some marks. So I'm putting the possible maximum marks right now for you. So in case there's an issue in the exam, we can help you out.
So do we need to submit the slides or the?
No, not required. You know, what I have done is I have what my usual practice is for these assignments. I give you mark above 70 and 100, between 70 and 100 for everybody. So then we have some way, if there's an issue, to use this tool and then support you out. So I have already given you marks, Mr. But if you do well in the examination and the final presentation of this one, we need not to use this scale, so we can just throw it away.
So the one temple I told the last class regarding one Indian temple, I go through that one, sir. Hello.
Yeah, that's yes.
That is actually the shadow is casted on the building itself. It's not fallen.
Okay. Yeah. Can you share the screen, Joe?
No, I have the it's with my phone. So next time it's 1,000 years old. 1,000 years.
Right. Right. So if you can find the dimensions, model it in Blender and give it the location, and then see if they actually it doesn't cast shadows. Just check
okay.
it.
I got the location also. So
right.
We'll try one time. Okay.
Right. So next time, who is going to just remind me? I think Mahesh can remind me to give opportunity for Dunstan to do that presentation to you.
not next time, sir.
No, just I think it's just a pyramid.
I will give these details. Okay, sure.
It's just a pyramid, isn't it?
Sir?
It's just a pyramid, isn't it?
It's look like a pyramid, and as well as have some rectangular shape as also in the down portion.
Not difficult to model, isn't it?
It's a little bit difficult. It's a very big temple.
Is it?
Yeah.
Then what we'll do is we will get Ruan also involved in that one.
Okay, sir.
So, Yeah, so you can find the photos and then share with Ruan, so he will do the modeling. And then we will get Madhavi also involved. So Madhavi can do the shadow study. So I like the way she has done it.
Okay.
Right. So 3 of you can get together and do a small presentation next time. So we must start doing group work also very soon. So this is good you brought it up. Right. So next week we will for sure give you some time to do the presentation. So other 4 people, we will give another assignment like that next week. Right. Okay then. So we will then stop here and then we will meet next time. Right.
Okay. Thank you, sir.
Thank you, sir.
Thank you.